So, hello, my name is Roman, and the topic of my thesis is reconstruction of video and sign language dictionaries. This work was done under the supervision of Maxime. So, why is reconstruction and why sign language dictionaries? Today, virtual and augmented reality technology is becoming in trend. This is a popular thing, and this trend is increased demand for technologies of 3D reconstruction. Such 3D reconstruction and algorithms in general of 3D reconstruction can be obviously applied to many areas, but in the next 40 minutes or so, we will be focusing on sign language dictionaries. And nuances of work with sign language dictionaries implies, first of all, different sign languages, and second, that they are pre-recorded in dozens of different formats. So there can be different can be video, it can be images, and it will be really nice to have some universal algorithm which can take as input different sign language and reconstruct everything in one unified database. So such database then can be used for creation of a new type of educational content for people who want to learn sign language in VR and AR, where people will be able to see hands from different positions and from different distance. So to make us closer to emerging of such algorithms, we need to answer some questions and create some prototype at the moment. So we focused first of all on prototype, and then we answered also research questions which are aimed at solving this problem of multiple data types at the input. So actually, some of you who work with 3D reconstruction may say that it is convenient to use depth data, but the problem with that is video dictionaries was not pre-recorded with depth data, so unfortunately we cannot use this. And if you work with RGB, we can think about most of the methods of the market as modular approach, where we first localize hand, then detect 2D key points, generalize it to 3D, and add hand surface to make it understandable for people, to make the hand realistic, not just some cloud of points. And at hand localization, we start to see the pattern of usage of object of results refinement, which is often used. So when we want to solve some task, we can actually calculate results multiple times, and on each iteration make it with more accuracy. And the same thing is actually applied for stage of 2D key point detection, where one of the best performing methods is showed that we can in parallel calculate points and connection between points in case of if there's an image multiple people. And make it with refinement. So calculate different types of predictions with multi-stage algorithms. So then when we have localized hand, and then when we detect 2D key points, there is this task of like restore this information which was lost due to projection on the image plane. And authors in work using a single RGB frame for real-time 3D and post-estimation in the wild used this idea of that they can actually make projections of kinematic model of the hand and minimize parameters of that kinematic model in the way which optimize parameters of the model in a way which will minimize difference between projections of their mathematical model and detected 2D key points. But this is in a way double-edged sword, because we can use, in this case, information from previous frames for video sequences as a good approximation at before optimization. But actually, we then heavily dependent on detected 2D key points, which was before. So if we will minimize the wrong if we will minimize projection to the wrong 2D key points, then error will be kind of high. And when we have 3D points, how we actually create shape? There's different methods. For instance, we can use some model where we add in same amount of distance to each 3D point to create realistic hand, but one thing called Mano. It is a mathematical model which was based on around 4,000 of 3D scans, which can reconstruct realistic hand from set of parameters. So we treat it as black box and invest a lot of energy to somehow like reverse engineer it in a way to create this algorithms which would be able to find these parameters which will then be reconstructed to the realistic hand. And actually, not all approaches is modular in a way which I showed before. Some of them are kind of connect different stages together in the one stage. So on this slide, we can see idea that we can localize to decay points. They are localized almost universally with heat maps, and then use latent features from the middle of this network for decay point detection, and use those features as well as heat maps to reconstruct whole hand at once, and then regress those 3D points afterwards whole hand. So another idea was produced here 1 year ago in the same place where I'm standing now by Oля Chernetska, and in her thesis she proposed to calculate normalized 3D coordinates, this interesting idea to calculate first heat maps and then pass to convolution with latent features as in previous slide, and then to calculate normalized 3D pose. But the problem with this that we don't know, because those 3D points can be in multiple different scales. We risk to lose a lot of information when we passed already detected 2D points to those convolutions, then can ruin a lot of two-thirds of the information when we change some distribution by convolution. We actually can done it by mathematical, like affine transformation. It will be more reliable. So what are takeaways from all those literature? First of all, the model approach suffer from error accumulation, but we can actually solve it by usage of previous frames. And also we can connect multiple stages to make as much as we can from different, from those extracted latent features. And that refinement of results is a good idea to apply to different tests, and we can actually apply it to decay point estimator. And based on that, we set few hypotheses. First of all, that synthetic video frames will improve accuracy. I will say in a few slides what it is synthetic video frame. And then the refinement of results will help to maintain higher accuracy on different stages of computation. We work with 2 data sets. Actually, we searched and studied a lot of data sets, but the problem is that for some works, there's only like 18 points marked, for some it's 21 points. And if you want to train and evaluate network on different data sets, we need to be sure that all annotations are in some data format. So also, it is really difficult to create accurate 3D hand shape annotation because we need accurate 3D scanners. So often data sets are synthetic because hand is generated with the coordinates to some shape. And we use the thin hand data set for validation. It is convenient because we can, in that synthetic data set, we can swap background to anyone we want with high accuracy. And we use freehand data set. It is large data set of 30,000 images of real hands interacting with objects, which are recorded, which are annotated with accurate 3D shape and mono vectors of that full hand. So we introduce, let's say, 10.5 architectures out of 13 studied, because one of them is based on UNET, which is on the market, and 6 are for stage to decay point estimation, 5 for depth estimation, and 2 for this search of parameters of final shape. as the system is already at that moment kind of complex, we are decided to use the same metrics everywhere for training and validation to make results more readable. And so for each architecture, we tried video approach and tried refinement. So video approach is, because there is no pre-recorded sequence with 3D annotations, we, for some random frame, we choose hand with similar 3D configuration based on annotation and used it as previous frame of the video, and we passed ground truth annotation for each network. For some another hand, not one with for which we're trying to predict 3D. So that being said, there's three main patterns of the architecture. Yellow boxes represent number of predictions. So in that case, this is introduced by us network twice small as UNet. UNet is popular network for segmentation and K-point detection. And so for each of those networks, black box represent input, and we tried both single image input and a couple of frames as input to test hypothesis of synthetic video frames. And as you can see by the architecture, we tested refinement hypothesis because we calculated results multiple times for some of the network. And take in mind that this network is almost twice as small as UNet, because in the middle we have 196 feature maps in contrast to 512 in the case of UNet. So then the stage of depth estimation. So we decided not to lose information after we detected 2D key points, to generalize it to 3D by adding depth to each key point. Here we again testing video hypothesis and refinement hypothesis. In all cases, this is introduced by us architectures, which is started from feature extractor, the set of convolutional layers, followed by set of fully connected layers, where in case of video work with video frames, we have this additional black marked as black boxes neurons, which are additional input of ground truth for some another hand in the video sequence. And yellow boxes is additional outputs, which is kind of refinement in the case of set of fully connected layers. So then we need to somehow find this parameterization of realistic hand surface. And first we tried a lot of different multi-layer perceptron type architectures with dropout, without dropout, multiple depths, but in the end we found that all of them failed to find those parameters based of 3D key points. And it was decided to use networks similar to networks used in language translation, where we have one sequence and we need somehow to translate it to some new space. So in our case, there's kind of like a sentence. Our hand is, so we use a sequence of 3D points as sequence of words in a sentence, and use a long short-term memory cell to translate it to a new space. And I will show in a few slides how it works. So we tested, all those results are in validation dataset, which wasn't used in train or testing. And so it wasn't in testing like to find final metrics. And we showed that in all cases, usage of synthetic video frames on different architectures improves accuracy from 28 to 46%. And for single image networks, we showed that refinement is each time improve accuracy. And as I said before, even though STH is twice as small as UNet, almost by amount of trainable parameters, it's still more accurate than UNet. And what about depth estimation? Depth estimation in synthetic video frames again showed increased performance, and we tested results from both single image and video sequences, and we can see here kind of interference between usage of both techniques, because if you use both video frames and refinements, they kind of in conflict with each other, and we only improve accuracy by like 1% for video sequences, but almost by 11% for the case of single RGB image. And then LSTM showed almost twice as good performance as multi-recursive on two tasks of shape parameterization. But it is interesting that that addition of shape, when we translate 3D points to parameters and then reconstruct it again in a hand, those final 3D points are deviated a bit from input 3D points. And for trained data, this deviation is around 4%, but for validation data is 13.5. And it wasn't intuitive at first sight because we didn't use any textures for shape parameterization, and it doesn't need to be it's not so affected by overfitting as convolutional networks in that case, but we actually will see in a few slides why that. So for trained data, we showed that even for cases where finger is occluded by some object due to camera position, so this is a reconstruction from another view, we see that in all cases we have projected 3D reconstructions. But because we didn't use augmentation and wanted to test hypothesis in simple environment, it didn't generalize so well for complex situations with different backgrounds, and we used blur to make sure that we have some accurate result here. And we see that when we add shape, almost always this stage of shape parameterization trying to make hand more anatomically correct, which is actually good for our educational content, which can be created in the future. So when depth estimation to decay point detection produce some non-reasonable cloud of points, which is not actually related to labels, then when we add in surface, this LSTM network in a way tries as hard as possible to translate to that feature space parameters in a way which will be understandable as hand. So actually, when we tried an American Sign Language data set, in a lot of cases it was failed to create correctly 3D points, but in some cases we see those characteristics of denoising of addition of shape, because in the case of A, index finger was not detected correctly, but when we added surface, actually this shape parameterization which we introduced actually reconstructed one of the fingers and made more anatomically correct hand. So as achievements, we can consider that we introduced its LSTM network for shape parameterization, which wasn't, which we didn't find in literature. Then we tested hypotheses for video sequences. We tested hypotheses for shape for results refinement, and in conclusion, we showed that video frames improve accuracy, but refinement is in a way interfere with the usage of video frames, and it works nice only for single images. As was mentioned by Riazantsev, I'm not sure, reviewer, sorry. It is the next right step is actually to retrain system with data augmentation to make it more generalizable well to multiple data sets and different sign languages. And after that, we will be able to compare it with state of the art on certain data sets. And at the moment, network only works with one hand, or system of networks rather. And it is needed to add detection of second hand to be able to work with more complex hand gestures in sign language. So thank you for attention.
Така фраза, тому що tested on validation dataset and accuracy.
Я маю на увазі, що Я там заговорився. Там ідея в тому, що ми додали блюр для того, щоб коли ми зробили цю 3D-реконструкцію, ми були впевнені, що вона зроблена на складному зображенні для нейромережі. Тому ми свідомо зробили більш складним випадок з додаванням блюру.
Тобто у вас якось є окремо, власне, бачите, це тренінг, тест, validation.
Yes. So, for each stage, we tested everything on trained dataset, test dataset, synthetic and dataset without augmentation, certificate with augmentation, and use mean squared error and L1 for final points and heat maps. And we tested for each stage. And this is final solution, which we aggregated from the best network to achieve higher accuracy. All networks were trained with the same amount of hyperparameters for the same number of train steps with the same.
Там відбувається знову ж таки питання, багато буває.
На слайді.
Так.
Ось тут конкретна конфігурація у нету. Тут
розумієте, просто дивіться, важливо, тобто в неті є декілька важливих речей. Перше, це є п'янчики. Коли, наприклад, важлива річ, чому симулюють, як звужується і як розширюється. А насправді, тобто звужується, воно стандартно, це якась архітектура для класифікації, розширюється, вона якимось реальним транспортом. Є важлива частина bottleneck, насправді, яка між ними знаходиться. Тобто, які там bottleneck? Там є bottleneck, нема bottleneck. Як ви знову ж таки, я так розумію, що це майже, це, по суті, задача сегментації цих точок, правильно? Які лоси ви використовували для цього? Тобто, наприклад, там, не знаю, якийсь local loss, там, наприклад, щось.
Тут тільки mean squared error by heat maps.
Просто насправді там, якби, чомусь всі це вважають класичною задачею, але при тому там насправді, покращення там в якійсь сегментації можна робити просто брати готово, скажімо, всі дуже так тривіальні до цієї задачі, там, по сегментації, там багато спробувати.
Так, звісно, можна багато зробити нетів. Ми вибрали один з них. У нас не було часу перепробувати ще, окрім цих 13 архітектур, ще 10 унетів. Це б було більше.
Можна було експериментувати з лосами. Тобто, мені здається, просто якщо ви брали просто звичайні місце error.
We experimented with losses a lot in task of shape parameterization because it was really difficult to find those parameters from. So in this stage we have those 3D points, and then we somehow trying to translate it to a vector of parameters, and we used loss of. So we can actually use loss of k points here, and we tried both only loss by vector and loss by final shape prediction, and we tried different approaches of training such systems, but in the end we found that in a lot of ways over complication of those stages results really difficult tracking of error, like from where error is on which base, I don't know. So we in the end decided to use the simplest case of everything because the system is large and it's becoming harder to track of error origination. Stage, yes. End-to-end тренування з final. Because we wanted some prototype at the moment. So you can see that ID of this network is AB, which implies that it's both A and B networks trained simultaneously, and yes, so we trained end-to-end. Yeah, so for AB, for final, because if you would train end-to-end,
реконструкцію, реконструкцію, І тобто це все типу end-to-end, тобто у вас, ну, знову ж таки, важливо, що зрозуміти end-to-end. End-to-end означає, що вони там типу одночасно відбуваються.
I get it. So,
ну, просто це насправді це важливий внесок, про який ви не говорили, що воно змогло все так, ну, окремо, ми вирішили одну задачу, окремо іншу вирішили задачу.
It's divided to two. We started to aggregate stages step by step. So we only trained end-to-end A and B because this network for shape parameterization is actually we wanted it to train of all types of poses. So this LSTM. So we didn't use it end-to-end because we didn't want it to overfit on certain hand poses. We want it to be really well generalized. But the first stages of 2D key point detections and depth estimations, we actually trained end-to-end because it is one task. But for the testing of hypothesis, we separated it because we wanted to see influence on each stage of each hypothesis. Because if we would, in a way, glue them together, it would be hard to track how video affects one stage and segment and the refinement affect another stage, because it would be one stage. We would not be able to track influence of.
More questions? Є у вас розрізнення правої і лівої руки? Я бачу переважно права рука.
Так, на даному моменті ні, це частина майбутніх досліджень.
І теж тема роботи у вас звучить 3D Reconstruction of Video Sign Language Dictionaries.
Yeah.
Але я бачу, що ви чи створили, чи ви показували нам кілька літер, кілька знаків, які ви відтворили, чи протестували ви на чи Dictionary фактично створений якось, чи реконструйований, так, чи які окремі якісь?
This is actually dictionary, and we added this is actually dictionary of letters. So it's a style of sign language called fingerspelling, where people want to show their names, they show a name letter by letter. And
для всіх маєте.
But the problem is that for most cases it's incorrect. So we shown here that it's not working as it could work in the future. But we added video because we tested a lot of architectures for video analysis. So we wanted in title of the sets represent different aspects of the work.
So one question for slide number 23. So this person's, what are they?
So this is when we have those key points, and we pass it through this first when we parameterize it by recurrent neural network and then reconstruct again by manual, we can actually measure position of new key points. And this is deviation. So when we have here 163 key points, and then there is another 63 points, and different this loss due to parameterization.
So we want there to be as less as possible.
In a way, but if those key points are incorrect, for instance, as it was here, we didn't have here any points for index finger. We actually wanted to deviate in a way to represent anatomy of the hand. So because the system is modular and because the system is modular and the error is accumulated. So if this is incorrect and we pass it here, so we want to add something which will be able to denoise previous steps, and this parameterization is a way out.
And the first point in conclusion, you mentioned the synthetic video, and somehow I missed it in the presentation. So how do you use this synthetic video?
So because there is no sequential data set recorded with all annotations. We used data set of images where we have some random image for which we want to predict, and we use some really similar image from data set as previous frame. So we sorted all annotations for smooth transitions. Yeah, so we sorted by 3D, by similarity of 3D position. So we have some annotation for that hand, and we find the most similar hand for with the most similar 3D position.
So we have one hand in one data set.
No, that's all in one data set to apply. So for each data set, when you have those train indices, we trained all trained subset. For test, which we sorted only test. For validation, sorted only. So we mimic smooth transition of real videos because we don't have real videos. We needed to do that. Because what?
We simulated video processing using this.
Yeah. Because we don't have video, we needed to work somehow.
So, but in terms of input, do you use synthetic video?
Yeah, we using this. It's similar to if in video, one frame would be annotated. So if it was application which designed by someone who worked with sign language, they could actually annotate one letter. And we are passing to network this one annotated hand to show the network which texture is represented to what, and then, so if it's this ground truth, this hand, please predict this new hand. Okay. So this is idea, synthetic video frames.
Okay. More questions? Yeah. I just have some remarks. But just common fallacy for all the presentations. When you present results in numeric form, for instance, you do not even mention whether the results were good, bad, and why. For those people who are deep inside your topic, it might be okay because they know what is the best result ever to compare. Those who are a little bit outside, that might be difficult to judge, isn't it?
In a way.
It's not only for you, it's for all those who are going to present today. Okay?
Yeah, that was my question actually.
In fact, I'm just elaborating and emphasizing this stuff because it is important for this defense presentation. You have to show what was your achievement. You just labeled it without any explanation. That's not good.
Do I need to comment it or?
No, that was a remark. That was not a question.
Next defense, they will be all right.
You may defend yourself if you wish. By saying no, I did a remark and did my best to show that this is excellent, this is the state of the art, unreachable by all the rest. Was that the case?
Was state of the art?
That you became a champion in 3D reconstruction of
for trained data set. For trained data set for sure. For validation also.
For this synthetic data set.
For synthetic now.
For didn't. Okay, so you have a lot of things to do.
Yes,
also
I'm
including
not.
This dictionary reconstruction, isn't it?
Yes.
Do I interpret it correctly that the overall objective of your work has not been achieved?
It was achieved because we want final goal is to create this educational content. We divided this path to this final perfect content into small sub steps, and we moved as far as we could. So if it was obtained, it wouldn't be master status, I guess. I don't know.
Okay, thank you. May I have your clicker?
Sure.
For a second. I can tell you a secret. There is a laser pointer here.
Oh, this.
That's for everyone who's going to present. One more thing. When you talk to the audience, talk to the audience, not to the screen. Thank you.
I was nervous.
Me too.
That's not an excuse.
Маємо до сих пор
Все буде добре.
Найкращий диплом. Я хотів проклікати презентацію, подивитися, що
Раніше треба було приходити.
якщо все не потрібно.
Мене, до речі, писав. А, це я ж.
До речі, у мене давно легко. Це не моє. А що, ти почути не можна? В мене
Це основа, але
це рівень міністра, який не може почати презентацію. Чи не заспойлили нічого?
ми спали.
Не дивіться. Чи все під індією готово?
У нас кожна сторінка з'являється окремо.
Дякую.
Може було у вас.